Ever wonder how to apply surface pressure loads on complex 3D geometries in STAAD.Pro? Or why your flow load sometimes skips certain members? See, today we are diving deep into one of the STAAD's most powerful yet underrated features, that is the enclosed load. Now let's first understand what is enclosed zone. See, an enclosed zone in STAAD.Pro is basically a closed polygon formed by the vertex nodes. You can imagine it as a boundary or a closed loop or on any 3D surface like floor, wall or roof on which you can apply pressure loads. Now see, unlike traditional flow loads, enclosed zone loads are much smarter. They can handle convex corners, openings and even complex or irregular geometries in your structure. Now, why do we need this? Because see, when your model has complex surfaces, STAAD's normal area load might skip corners or cause orphan areas where loads are not applied correctly. And that's where enclosed zone comes in handy. So let's understand these few points like boundary node selection and the load direction. See, when defining an enclosed zone, the sequence of boundary node is very important. See, you can define them either in the clockwise or anti-clockwise, and this direction determines how STAAD applies the load. And here is how. See, if you select the nodes in the clockwise order, the local z-axis of that zone points into the plane. And if you select the nodes in the counterclockwise order, the local z-axis points out of the plane. And to visualize this, we use the right hand screw rule. See, if your fingers curls in the direction of the node selection, your thumb points in the direction of the positive local z-axis. So if your thumb points up, that's your positive load direction, and if it points down, then that's the opposite. The next important part, load transfer mechanism. Now see, once you define your boundary, I have shown the sample STAAD over here. You can see STAAD divides the enclosed zone into smaller sub-panels. These are like mini patches created between members and openings. See, each sub-panel is analyzed based on the yield line theory using the angle bisector principle to find the load influence area for every member. See, each member within the zone then receives the load as discrete point loads. STAAD divides each member into 16 equal segments and apply loads at the centroid of each load influence area. See, if the part of the load influence area extends beyond the member, the load is applied to the nearest end node. The most important part, member ignores for the load transfer. See, you can also specify certain members as ignored for load transfer. These members wouldn't receive any load. Instead, their share gets transferred to the adjacent members. And this is super useful when you want to simulate one-way slab behavior or exclude beams from the load sharing temporarily. But be careful. See, if you ignore members at the boundary edges, you might create open subpanels which can result in missing load zones, and STAAD wouldn't apply loads there. Next important part, openings and subpanels. See, this is another cool feature. You can define openings within an enclosed zone. These are basically areas where no load is applied, representing things like stair openings, ducts or skylights. So STAAD will create subpanels around these openings automatically. And here are few limitations that you need to take care while creating your STAAD models. Of course, enclosed zones comes with few limitations. For example, maximum 500 enclosed zones per model. Each zone can have up to 500 boundary nodes. Each zone can contain up to 400 openings. Also, the zone name that we specify, it is limited to 15 characters only. While these are high limits, STAAD performance can slow down if your model uses too many complex zones. So it is recommended to keep the number of nodes per zone within about 80% of your total model nodes for the better efficiency. So this is one of the most important aspects you need to take care while creating your model. So that's the basic working and setup of enclosed zone loads in STAAD.Pro. I'll give you a short brief on how to create these enclosed zones for all three categories through this sample model in this segment. Okay, so now you have understanding about the enclosed panel, its parameter and their limitations. Now, so let's understand how this actually works in the model part. So to make you understand, I have considered these two different models. Okay, and one of the important thing I want to tell you that this particular option is available from the STAAD.'s 2023's version. It is available. Okay, so make sure you have that particular component version in the connect edition, so that this option you is available. In the previous version it was not available. So once I click on the enclosed zone definition, I can click on the add, and once you click on the add, here you have these three categories: boundaries, openings, ignore member, and the loads on the member. So we will go through one by one segment. Let's say if you just want to create a boundary and apply a load, so I'll click once I click on the tab over here, enclosed zone, click on add, and here you can provide the name as well. Let's say if you have multiple floors, you can rename these zones as floor 1, floor 2, floor 3, or with respect to level, let's say level 3 meter, level 6 meter, level 9 meter, something like that, so that you can identify all the zones quickly. It might happen that you have multiple number of zones on the same floor, right? So depending upon your area which you have on your building, let's say on the same floor, when you have the library section, just giving you a random example of a, let's say a college building, you have the library section, or you have the classroom section, or you have a laboratory section. So likewise you can identify those zones because of the differential geometry. You can provide the name over here. Here right now I am keeping this as zone 1 only. Okay, here you have option to select it directly from the model, or else you can directly enter the nodes. So we will go with the node list option over here. Now to select the boundary, you have two options. Okay, either you can go in the clockwise direction or in the anti-clockwise direction, right? These things I have already given you about the brief how this orientation work for the panel segment. Okay, we will prefer to go with the uh, anti-clockwise direction. Okay, so I'll click here, I'll select this terrace segment. Okay, I'm moving in the anti-clockwise direction. You can see the numbers are identified over here, right? 23 to 25, 22, 22. Okay, now make sure you start with the anti-clockwise position. In that manner the local z of the panel will be up. Okay, and load direction will be according to that. If you model it in the clockwise direction, your loading direction you have to take care. So make sure you start with the anti-clockwise segment. In the load definition as well it is specified. I'll show you here. I'll click on the add option and close. Here you can see it is in the anti-clockwise direction, right? So I'll prefer the anti-clockwise direction. I click on the add option. Again we will go here, enclosed zone, click on add option. I'm simply adding, clicking the cursor over here. All right, now I'll click on the add, and you can see the top segment is highlighted with the blue color. So this is your boundary. So once you created a boundary, now let's say I want to implement the load over here. So I'll click on the first load case, I'll click on the add, and here in the load list item you have this enclosed zone option available. Now as you can see over here, the panel formation is shown over here in the anti-clockwise direction, right? So your Z is up, that is Z positive. Now I want to apply it in the downward direction, so I'll enter -2 over here. Here you have this list of zones available. Currently we have created only one zone, so it will be available as single zone only. I'll click on add option, and you can see the load is implemented correctly over here, right? You can reduce the scale of the loading if you, I'll reduce the force values over here. If you want, you can reduce like this. Okay, so that's how the first segment is created, right? Now let's talk about the other case. So I'll go to the next phase in the next floor. Still upper zone segment is available. Okay, now I will create the another zone. Now here we will go for the, let's say, uh, opening part. Okay, if you feel in your structure you have the opening, so you can create a different boundary. So let's see, we consider this particular structure, let's say we will consider this as an opening. So what I'll do, I'll create another boundary element. Okay, and let's say we will select this here. I'll click on the add option. So here we have one boundary. So this is a slab formation. Now assume that we have opening over here in between this member, right? So I'll click on the zone option, I'll click on the edit option, and then we will have this option available. Now it asking for selecting on model, so I'll select nodes here. Okay, so this will be our polygon nodes for opening. I'll click on the modify option. So here it has identified as an opening, right? Now let's see how the loading part works. So for the opening part, I'll click on the enclosed zone option again. I'll select my zone 2. I'll enter the load value as -2 and click here. You can see the load is applied to this particular and this particular portion. This segment is remained empty. Let me show you in the plan view. Okay, so it is looking something like this. So it has considered this as an opening. So we have all those limitations in your floor load option, but yes, utilizing this option, you can work out like this, right? So I hope the other option of creating opening is clear to you. All right. Now let's understand the third option. I'll delete this just to give you the other option idea. I'll delete the opening as well currently to make you understand the next part. All right. So in the similar zone here, if I click on the zone option, then we have this next option as ignore members for panel formation and ignore member for load transfer. All right. So what is this understand one? Let's understand one by one. So the first one is ignore member for the panel formation. So let's say I'll select these two member. Let's say this and this. Okay, so what ultimately it will do, it will ignore these two members and assume this as an entire panel. This is something like that. Okay, boundary is full, but it has ignored this two member and it will assume this as a full slab panel, ignoring this two, right? So if we apply load, what happens? Let's see. Enclosed zone, zone 2, I'll enter the value -2, add. Right now you can see the load formation of the two-way load distribution. You can observe it has considered this as an entire panel and they have ignored this two members, right? So this is what it means, right? Now let's go and understand the other option, ignore member for the load transfer, right? So currently the load formation is transferred over here, so we will understand that other part. Let's say in this particular building, I'll choose the different building, but let me show you first
if we do not have ignored this member, how it will form. So I'll delete this ignore members, and now this is the entire boundary and how the load formation looks now. See, now the load distribution is for each panel, it has considered the two-way slab distribution, this 1, 2 and 3. So that's how it looks. Earlier we have asked STAAD to ignore these two member and consider this as a full element or the full panel. It has considered like this. So this is the major difference for this, right? Now similarly for this case, if I ask STAAD to just don't consider beam number 77 for these loading part, right? So I'll ask them that ignore members for load transfer. So I'll select this and I want STAAD to don't consider that particular for the loading, and you can see the load distribution is now different because STAAD has ignored this member. Now you can see this panel formation is up to this. So this is considered as an entire panel. Load distribution is here. It has ignored this member and this panel is separated. So I hope this is clear to you what does each of these categories means and how this works, right? It's easy to understand this. So we have covered openings and we have covered ignore members or the ignored members for load transfer and ignore members for the panel formation as well, right? So it's quite simple and easy. Once you are able to understand, you can work out for all the categories depending upon your requirement. Hope this video helps you. If you like this video, go share to your fellow engineers and your batchmates. And always remember, don't just learn software, learn concepts. Thank you. Wait for the part 2 as well. Stay tuned, keep learning, keep sharing.
In the next part, we will understand how yield line theory, load discretization and geometry limitations affect the load distribution, including how to deal with concave shapes and orphan areas. So let's into that particular part 2 in the next session. So till then, keep learning, keep sharing, stay tuned and always remember, don't just learn software, learn concepts.